and specifically the topics that came in the exam, I actually covered up to this slide probably. So it was related with the limits associated with the gating functions and some other functions, mathematical functions that may arrive in the modeling of the exciter system. Okay, so then let's continue from here. So besides that protective circuit, we can also have another block. We have already discussed this part before meet, but let's continue with whatever diagram we have here. So the blocks are shown here. So this is again the exciter or the main generator block actually. So this is the main generator block, that is the synchronous generator block, the field of which is actually controlled by the exciter over here. And again, the exciter input or the deviation in exciter input is again regulated by the voltage regulator over here. And the voltage regulator will take the value as the input of the voltage regulator would be simply the output of the load compensator. And the load compensator is again modeled by a series combination of an RC and XC elements, where both of them are kept as variables. So if RC and XC, we don't want to consider RC and XC, that means if we are explicitly interested in controlling the terminal voltage of the generator, that is represented by ET over here. So in that case, you simply make RC and XC shorted, okay? And accordingly, the same signal would be passed through this load compensator block, and the voltage regulator will treat the error in ET. Otherwise, if we are interested in any other potential within the system, okay, within this system, then accordingly we could set RC and XC to be both positives or negatives. And to calculate the output of the load compensator, what we can do, we can simply take the sampling of the value of the terminal voltage through the help of the potential transformer. This is one input to the load compensator, and another input can be traced or can be detected with the help of the current transformer, that is the terminal output current from the synchronous generator. So these are the two input, and with the help of these two inputs, ET and IT, the output of the load compensator would be calculated. The output is simply VC1, and that is nothing but the absolute value of this ET plus RC plus JXC multiplied by IT. So ET is this voltage, and whatever drop is there due to the flow of IT through this load compensator block, that would come up as the VC1 output of the load compensator. And then if you use the voltage transducer, then with the gain 1 and a time constant TR, then this is the final output of the load compensator block. And that VC would be actually fed to the voltage regulator. So if we look at the overall excitation system now, and if you remember, we were specifically discussing about the IEEE DC1A exciter. So this is the complete block or the overall block, where this block, to start with, if we look from the right, start from the right side, then this block takes into account of the saturation. So this is the saturation modeled. And then this is the exciter time constant TE, and this is the exciter gain KE. And we have already derived what are the expressions for TE and KE. And these signals are actually fed back at this summing junction. And this input VR is actually the output of the voltage regulator, and this is simply the voltage regulator block. So the voltage regulator is simply modeled as an amplifier with gain KA and time constant TA. And these are the limiting functions, VUEL, under excitation limiter, and the position of the under excitation limiter could be placed here, or it could be placed at the summing junction, the second summing junction. There are two summing junctions to start with. And this is the high value gate, means whichever value among these two, between these two is higher, that value would be passed. The amplifier has a certain upper limit and lower limit based on the practical constraint of the amplifier blocks. Okay. And this is this block. This is the lead lag block. This basically represents the inherent time constants of the exciter, which we actually haven't discussed in detail of the exciter. But fortunately, in the model itself, what they prescribe, the IEEE, the committee prescribes that we can easily take TC equals to almost equals to 0 and TB almost equals to 0. Means actually they can be neglected. For our purpose of analysis, both TC and TB could be neglected. So in the next diagram, when we will be simplifying these blocks slowly, we'll be actually getting rid of some of the blocks and some of the limiting functions as well. Remember, our main interest is in some linearized model, because we are trying to capture the small disturbance stability scenario. So accordingly, we are actually not interested in any of the limits imposed. Okay, so whenever you say there is any limits imposed, means we are actually going into the non-linear zone of operation. So like when the system operates at VR max or VR min, the linear relationship between input and output no longer remains valid. So because we will be working in the linearized zone, so either we will be working here or we will be working here, so that we have a simple relationship like y equals to mx, something like that. Some linear relationship in the steady state. We have some linear relationship between the input of this block and the output of this block. So any limiting function and these gating functions would be ignored. This lead lag inherent time constant blocks would be ignored later on in the next slide. So what else is there? So this is the rate feedback block. Rate feedback stabilizer block. Why it is rate? Because of the presence of S. This is known as the rate, and it is a feedback because you see this signal is actually taken as a feedback at this junction, at the second summing junction over here. And it's a stabilizer because we discussed earlier that without this, under open circuit condition or under no load condition, the generated stability is hampered. So that's why you introduced this block in DC1A exciter specifically. So in the second summing junction, we have 3 signals coming up. One is the output of the rate feedback stabilizer, that is VF. This is one of the signals. Another signal is the under excitation limiter. So you can see a star sign. So either it would be placed here, or it would be placed here at this point. And the third input for the second summing junction is basically the function of these 3. So VC, if you go to the previous slide, you know what is VC. VC is the output of the compensator. So you can see finally the compensator provides us with VC. So once again, the transducer time constant TR is pretty much negligible. TR is negligible. So you can easily say VC1 is actually equals to VC. So this is actually the output of the load compensator. So this VC actually goes into the summing junction. The next diagram, we will see where is the VC. This is the VC. Okay, so this signal is actually coming from the load compensator. So if you have a load compensator LC in short, then this is the VC. So then we have Vs, another input, and this Vs would actually come from the power system stabilizer. We will take this topic later on, but in short, this is power system stabilizer. In short, this is PSS. So the output of the power system stabilizer would be treated as the Vs. We'll deal with this in detail later on. And the V reference, as we discussed earlier, there are VAC reference, AC reference, and DC reference. So these are the reference voltage which would be tracked by this overall excitation system. So this is in short the discussion of the overall excitation system, but slowly we will be moving into the simplified version. So for our purpose of this simulation, in this course, what we will do, we will not go into the detailed modeling of the exciter as we have shown over here, but just for our background understanding of excitation system, we have taken all these things, all the modeling parts in detail. And now what we will do, as I said, we'll be getting rid of the limiters. So here what we are doing, we are simply ignoring 1 plus STA over 1 plus STB. So this block is no longer here. What else we are doing? We are ignoring the VR max and VR min limit. Remember, these two are the maximum and minimum limits associated with this amplifier block. So those are no longer considered. So we have a simplified block of IEEE DC1A exciter, now without limits and without the inherent time constants, these two, TA and TB. And also we have got rid of the HV gate, the high value gate. So after ignoring these three, we reach here. Okay. And then from this block, what we can do simply, we can bring out the state space modeling for this overall block diagram. So what we already know, we know what is Vx. So we start with that. So Vx can be represented by this exponential function along with these two constants, AEX and BEX. So Vx is an exponential function of the field voltage, field exciter voltage output, EFD. So this is Vx. And then we can simplify this block over here. So you see we have VR, and these three blocks can be taken together. So if we can simplify this, so this, for this overall block, this is the output EFD and this is the input VR. So between VR and EFD, we can write the transfer function EFD divided by VR. So whatever transfer function we have, that would be this block. And then if we simplify, we will get this one. Okay. So by now you should know how to get the simplified version out of this input by output representation of the transfer function block. So this equation basically deals with this input, this output, and this block over here. Then we have another state resulting from this block. Again, here this is the output and this is the input. So again, for this block, we can write in the similar manner. We can write VF over EFD equals to SKF divided by 1 plus STF. Again, if we cross multiply and if we simplify, then we should get this one. Okay, so while trying to obtain this, what we have used the relationship over here. So you can see clearly that if we cross multiply this, you will get VF plus VF dot. S means it is in the Laplace domain. It is d over dt, the first time derivative. So this would become VF plus VF dot TF equals to EF d dot KF. So you have got EF d dot, and simply you use the right hand side of that expression that will be multiplied by KF. So if we replace that, then you should get VF dot. And the last one that we are left with is this block over here. And again, our output is VR and input is whatever signal is coming as the output of this summing junction. So the output of the summing junction is simply this one that is written over here. So we have VREF. So we have VREF, the positive input to the summing junction. VS is another positive input to the summing junction. And there are two negative inputs. One is VC, another one is VF. So VC and VF. And with that, this is the input to the block. This is the input to this block. And this is the output of the block. So you can simply write VR divided by whatever we have, VREF minus VC plus VS minus VF equals to KA over 1 plus STA. And then again, if you simplify this, you should get this. So that means after ignoring the limits and also ignoring the inherent time delays or the time constants within the exciter block for a DC 1A exciter IEEE model, we will get some additional 3 state variables. So out of this overall excitation system, with this assumptions, like ignoring the limits and ignoring the time constants, we will get 3 additional states. Now, are we going to use this third order exciter model into our system? Probably not. So we will be going for further simplification. But well, if you are asked to find out the steady state values or the initial values for these 3 states, can you do that? EFD, VF, and VR. So if it is asked that find out what is EFD naught, what is VF naught, and what is VR naught, can you do that? Anyone interested in answering the query?
So it will be initial value condition calculation.
Yeah, so how would you proceed? Let's say the EFD naught, we have already done it in our third order model, right? Third order flux decay model. So we got some value of EFD naught earlier there. So just leave it there. We have got it from the third order model. We got delta 0, omega 0, and EQ prime 0, as well as EFD 0. Now, well, so if we know EFD naught, so can you find out what is VF naught and VR naught? So how will you start actually? I just want to know that from your side. How would you start the calculation? If you're looking for the steady state value or the initial value, what? Sorry? Again, please.
G by dt Vf is equal to 0.
Yeah, so all the derivatives that we have, all the derivatives in these 3 equations, you simply take it to 0, because in a steady state, there shouldn't be any dynamics, okay? And after that, probably you will get 3 equations. And of course, you need to know the remaining variables or the remaining parameters. Those are appearing on the 3 equations. after you take this equals to 0, this equals to 0, and this equals to 0. So of course you will get some equations, okay? And then you have to continue with your calculation process to find out this VF naught and VR naught. Of course, if we start from here, what do you need to know? You need to know what is your AEX, okay, and what is your BEX. Of course, those would be dependent on some operating point, and hopefully those would be given in your machine data along with the in the exciter data part. These two values should be given, AEX and BEX. So if those two are given, if you know EFD naught, then you should know VX naught. So VX naught is known. So that means this is known. Then KE, this should be known. This is the exciter gain. Exciter gain. This should be known. So this should be known. This should be available. EFD naught, it is already known. So you can see clearly that you know KE. If you know KE, if you know EFD naught, as we did earlier, we calculated. VX naught can be calculated only if you know AX and AEX and BEX. So if you know both of them, if both of those are available to you, then you can calculate VR because this side is 0. So you can know VR, and that should be your VR naught. And in the similar manner, you can proceed on. Okay. So you see VX naught is known, EFD naught is known, KE should be known, VR naught now it is already known. So you're only left with, okay, KE and TE and TF, this should be available. These are associated with the blocks, okay, either gain or time constant. So this should be available in the generator data sheet. Okay, in the exciter part, in the exciter dynamic data sheet, this should be available. So then you can calculate VF, which should be VF naught. And that's it. So if anything else is remaining, means what should be your VREF? So let's see how you can do that. VF naught is now known from here. VR naught is known. VS, power system stabilizer, if we are not using it, so simply take it as 0. The compensator block, so that means if you know compensator block output, then you can calculate VREF, or you can actually establish some relationship between VREF and VC. So in the steady state again, in the steady state, your compensator block output, you can clearly see, if we look here, the compensator block output, if we assume TR is approximately equals to 0, and also in steady state, VC1 and VC would be exactly same, okay, because in steady state, there won't be any effect of this Laplace as variable. So VC1 would be exactly VC. So you can clearly see how you can calculate VC. If you know ET, that is the terminal voltage of the generator. If you know the current output, the terminal current output of the generator, then if you know RC and XC, then you can easily get the steady state value of VC. So once you know VC, then you can come over here and you can put that value of VC here. So to know VC, what you need to know ET, IT, RC, and XC. If you know all this, then you can calculate VC. VS for the time being, consider it to be 0. These are already calculated, so you know what is your VREF. Of course, KA and TA should be available in the generator data sheet. So this is how actually you can, if required, you can also model this whole system, and you can also calculate the initial value for the resulting states from this overall excitation system. Okay, but for our course, what we will do, we'll be going for further simplification. And what we will see, actually, the simplified model is pretty straightforward, actually. So let's see. Okay, so the one that we have here is still it is not a linearized model because of this. Can you tell why it is a non or why it is not a linear model or linearized model? Can you justify whether it is a linear model or a non-linear model?
So SE is non-linear and also 1 by STE. These are non-linear terms.
1 by ST is not a non-linear term. SE, yeah, this is agreed, but this is not. This is a linear term. This is simply 1 upon STE. This is not a non-linear term. T is simply a constant. Let's say if T is 5, it is simply 1 upon 5s. So it has nothing to do with the non-linearity. But this is non-linear. Why? Because you can clearly see that Vx, it is a function of EFD, the exciter output voltage, and it is an exponential function. So clearly we all know that exponential function is simply a nonlinear function. Okay, the nonlinear function. So because of the presence of this, we can't treat this model that is presented here as a linearized model. So it is still a nonlinear model. Still a nonlinear model because of the presence of this exponential relationship between the output Vx here and the input EFD here. This is the saturation function actually. So the representation of the saturation, the way we are representing it is not linear itself. That's why the overall system is not linear. Okay. So then what we do, we actually did it earlier. If you can recall, we took the linearized version, we derived the linearized version of this block, these 3 blocks. We took the linearized version and we got this K over 1 plus ST. Where did we do that? Probably at the starting phase. So if we go to slide number 23, this is the DC exciter block diagram. This is the Vx representation. And this was the nonlinear part. And then what we did, we got the standard linearized form. Okay. And that was relating the change in exciter output delta EFD and the change in actually the regulator output or the exciter input, that is delta VR. So because all of them were represented as incremental variables, so we had to go for the linearized version and we did it in this manner. And we discussed this in detail, how to get this earlier. So now instead of those 3 blocks, we would be simply using this simple block, and that would give us this simplified version in the linearized domain. So this is the linearized version. So this is the linearized exciter block. This is the voltage regulator block. This is the rate feedback block. This is linear, this is linear, this was non-linear, now it has become linear. So the overall block is now linear. So this is, we can call the DC1A exciter block in the linearized version. Okay. So next what we will do, we will move away from this DC1A exciter, and what we will say that in our next part of the course, we will be focusing on a further simplified model, how it can be simplified or how it is actually simplified. So what we are assuming here, we are not using the DC type exciter anymore. Remember, there were 3 types of excitation system discussed earlier. One was DC type, one was AC type, another one was static type. In the static type, we didn't have any rotating device, rather we had a transformer. So we can clearly see that because of the presence of the transformer, we didn't use actually either DC machine or DC generator or AC generator as the exciter. Rather, the transformer was used directly. So there was no rotating device. Okay. So the dynamics of the rotating devices associated with the exciter block would no longer be valid here. So this is some, you can call it simplified ST1A. This is the IEEE model, but this is the simplified version, IEEE ST1A. So you don't see any exciter block here, okay? This is simply the voltage regulator block. Why we are not using any exciter? Because exciter system is nothing but simply a transformer, okay? It is simply a transformer, comprised of a transformer. So there is no rotating device. So we don't have to deal with all these things over here, okay? We don't have to deal with all these things. And because of the presence of the thyristor type rectification, so it is pretty fast, okay? It is pretty fast. So accordingly, we can only live up with this voltage regulator block, and there is no exciter block over here. So simply a voltage regulator block is enough to represent this IEEE ST1, static exciter type model 1A. So this is already in the linearized version. So you can clearly see that the inputs at the summing junctions, this is the del Vref, this is no more Vref, this is del Vref. So this is actually change in the reference input. So remember, we had two inputs, DC ref and AC ref, all those reference point of voltages. So this is the reference point, which reference voltage or reference voltage at the reference point, which should be tracked by the voltage regulator. So if there is any deviation, then this is the terminal voltage. Remember, we had, instead of the terminal voltage, we were actually dealing with VC, okay? Earlier, in the earlier diagram, we were dealing with VC here at the summing junction. So this VS was the power system stabilizer. VC was coming from the output of the compensator, load compensator, and this was the reference input. Okay, so what else is missing here? Before I move there, what else is missing there is the rate feedback, okay? Because the rate feedback is a special feature for DC and AC type exciter. So for the internal stability, for the DC and AC type exciter, we need the rate feedback, this block, okay? But for the ST type or the static type exciter, we don't need that, this rate feedback block. So that is also not available here. So it's simply a forward path transfer function block. It takes some error. The error is calculated between the compensator. Okay, let's keep it as the compensator voltage for the time being. Let's say this is del VC, and this is del Vref, and this is again from the PSS. For the time being, we are not bothering about this. So let's leave it as 0. So let's say del VS is 0. But for generalization, we can keep it in our representation. Del VC, we are not writing del VC anymore. We are treating it as del VT. How are they related? Del VT is nothing but the same thing as, it is, remember, is the terminal voltage. So if you look at slide number 32, you can see what is the relation between VC and ET. From this relationship over here within the block, you can clearly see this is ET, and we are calling it VT, the terminal voltage, okay, all the same. And this is the output of the load compensator. So this VC and this ET would be exactly same when both RC and XC are set equals to 0. That means it is a shorted path. Okay, that means we are interested specifically at the terminal voltage of the generator. We want to control the terminal voltage. We want to track the deviation in the terminal voltage from the reference value. Okay, so that's why we can easily write VT, that is same as VC, when this condition is true. And accordingly, we have written it over here. We have not written VC, rather we have written VT, and in the linearized version, it is del VT. Okay. So now it is a very simple block, and we would continue with this. We'll continue with this. So the derivation is again simple. So if we try to find out this equation over here, what we have to do simply you write the output divided by input. So that would be your transfer function. So the output is del EFD, and the input is you have del VREF minus del VT plus del VS, and that is equals to KA over 1 plus ST. So once again, if you simplify this, if you cross multiply this and cross multiply this, if you simplify, then finally you should reach here. So this is the single state variable resulting from the simple voltage regulator exciter block of IEEE ST1A. So instead of 3 state equations or 3 additional states, we can continue our discussion with a single additional state. So previously we had the third order equation for the generator. It was delta dot, omega dot, and EQ prime dot. Now along with that, we have, okay, if it is in linearized version, then it should be del delta dot, del omega dot, del EQ prime dot. And in addition to that, we will be having another extra state for the exciter block. So this is our 4th state variable. Okay. So now we see that if we look carefully, we said that, well, this should come from the PSS. We're not going to bother with that. Del VREF, it's a reference voltage. It is a fixed value. It's a constant value, but you can change it to any other constant value. Of course, you can change the reference set point, but it will remain constant there until and unless you are changing it from your side. So this del VT is now problematic, because if we look at the state variable list, these 4 are our state variables now, with the inclusion of the 4th state variable here, which is resulting from this block. So this del VT is actually none of this. Okay, so these are the state variables. So this del VT is actually an algebraic variable. So we have to get rid of this, and we have to take the del version, that means the linearized version of this. So how to get that? So let's see. If you remember the original expression of VT, there is the terminal voltage of the generator. This is the phasor VT. It can be decomposed into D component and Q component. So D axis component for VT is VD, and Q axis component for VT is VQ. If I take the magnitude of this phasor, so you can write it like this: VT, absolute of VT, or the magnitude of VT is simply square root of this, VD squared plus VQ squared, following the Pythagoras law. If I take square term on both sides, just with a target to remove this square root from the right hand side. So I take square on the left hand side. So on the right hand side, that square root is vanished. Then what I do, I take the time derivative on both sides, time derivative on both sides. So if I take the time derivative, then it is a chain rule. Okay, so first of all, you have to take the derivative of VT square with respect to VT, and then you have to take the derivative of VT with respect to time, T. So if you take that, then you will get this. If you take for VT square, you should get this. If you take the same for VQ square, you should get this. In other words, we are simply taking the linearized version, linearized expression for this nonlinear relation. Remember, squared, cube, all these things are nonlinear terms. So I'm linearizing this with the help of this. And for doing that, what you have to follow is you can take help of the Taylor series expansion. This is another way to say that. And then we try to simplify this. So we have delta VT, simplify. So just keep delta VT on the left hand side, and this thing remains on the right hand side. Then if you recall, earlier we derived the expressions for both del VD and del VQ. Okay, while we tried to derive the K constants, K1, K2, K3, and K4 earlier for the linearized model of our third order generator model. So these were the linearizing constants or linearization constants. So while we tried to derive these K1 up to K4, we had to take these relationships del Vd and del Vq, and we had to express those in terms of del delta and del Eq prime. And P1 and P2 are nothing but some constants which are based on system operating point or system parameters, the X parameters or the reactance parameters. So that means we can replace del Vd by this P1 del delta and del Vq by this P2 del delta plus P3 del Eq prime. This is already done in our earlier lecture. So then we can actually get del Vt expression in terms of two more K constants. Okay, two additional K constant would be introduced. So del Vt can be expressed as K5 del delta. So K5, what is K5? K5 is simply Vd0 over Vt0 into P1 plus Vq0 over Vt0 into P2. So this is your K5, and K6 is simply Vq0 over Vt0 multiplied by P3. So these are the expressions for K6 and K5. So in total, for this fourth order model, where the first three state equation belong to synchronous generator, the fourth equation belongs to the simplified IEEE static type exciter. So when we have the fourth order model, then you have to have 6 K constants. Okay. So previously we had 4, now we have 6. So with the addition of this state variable, we are trying to linearize these. We got a terminal voltage variable present in our state equation, which is none of these state variable. So we treat it as an algebraic variable, and then we linearize it, and we find the 2 additional K constants. So this is a summary of this slide. And then what we do, we simply replace del Vt by the expression that we have got at last here. So you replace del Vt by this K5 del delta and K6 del Eq prime. So that our overall expression is now simply some functions of K constants and some system parameters. Okay. So let's see how it would look like. So after replacement, what we get is simply this. So this was the original equation, delta EFD dot 1 upon TA, Ka multiplied whatever input is there from the summing junction minus delta EFD. This was the original expression. And then we replace this del Vt by del Vt is simply K5 del delta plus K6 del Eq prime. Because of this minus, we have these minus signs there. And then minus delta EFD plus Ka over Ta del Vref plus Ka over Ta del Vs. So this is your final equation. Now, with this, we should go for the representation of our model again in matrix version. Okay, x dot equals ax plus bu. So if you go there, then probably stop it here. And let's start whiteboard. So the equations that we had earlier are these. So we had del delta dot equals, this was the previous equations. We are just listing them. Del omega dot. So it was 1 upon twice h delta PM minus K1 del delta minus K2 del EQ prime. And of course, if you have any damping, then we can incorporate it here as this. But if there is no damping, then you can ignore this D to be equals to 0. The third equation was delta EQ prime dot, and this was delta EFD minus K3 del EQ prime minus K4 del delta. The last equation that we have got is delta EFD dot and delta EFD dot was equals to what? K5 and K6. What do we have? Let me see. Okay, it is minus KA K5 over TA. Reduce it a little bit. Okay. So this is minus KA K5 over TA. Or simply we can write KA over TA del VREF minus K5 del delta minus K6 del EQ prime minus 1 upon TA delta EFD. And we don't include the PSS term for the time being. Okay, so this is actually the fourth order model that we have got after including the additional state variable generating from the exciter block. So now what would be the corresponding expression for x dot equals ax plus bu? Again, we go there. So what is our x? Let's list that. So x transpose would be simply del delta, del omega, del EQ prime, and del EFD. Remember in our previous derivation, del EFD was not part of the state variable, rather del EFD was part of the input u, but now it has become the part of the state variable. So then you have u, so u transpose would be simply, what would be u? Okay, we have del PM, this is the mechanical input, and we have del VREF. This is the reference input variation in the exciter circuit, and del PM is the mechanical power input variation from the prime mover side. So now with this, so what should be the dimension of A? So A, the dimension of A should be 4 by 4. So now let's try to form A. Okay, so we have del delta dot, del omega dot, del EQ prime dot, and del EFD dot. Okay, so what should be the inputs, or what should be the entries for the A matrix? So delta dot so this is x dot equals ax, so this should be x plus bu. There are two of u, so that is del PM and del VREF. Okay, so let's list them: del delta, del omega, del EQ prime, and del EFD. So delta dot is simply omega 0, del omega 0 and 0, and there is nothing, so 0 and 0. Del omega dot is first it is del pm, so 1 upon twice h is there, then minus k1 by twice h, then minus k2 by twice h, oh sorry, minus d by twice h, sorry, it's a mistake, so minus d by twice h because of this, minus d by twice h, then minus k2 by twice h, and it doesn't have any delta EFT entry, so it should be 0. Del EQ prime dot is minus k4 over TDO prime del delta. There is no del omega. There is del EQ prime, that is k3 over TDO prime minus, and there is 1 over TDO prime into delta EFD, this one. Delta EFD dot, this is the last one. Okay, so here we don't have any of these inputs. So the final one, Ka by Ta del Vref. So this is Ka by Ta del Vref. Then minus Ka K5 over Ta. This is this. Minus, okay, there is no del omega. Minus Ka K6 over Ta. This is this. And minus 1 upon Ta delta EFT. So that's it. So you have the A matrix, which is 4 by 4. This is your B matrix. This is your U. And the dimension of B you can clearly see from here. So this is the representation, state space representation of your linearized model for this fourth order system, where the first three belongs to the generator again, and the fourth one belongs to the simplified exciter block. Any question up to now? No question. Okay. So now this thing, we have to run it and we have to see what is the response. What benefit, or are we getting any benefit out of this with regard to stability scenario? Okay, so let's see the simulation. So this is the file. Do you see the MATLAB window?
Yes, sir.
Okay. So this is the same file actually that we did for the third order linear third order single machine infinite bus system. Same data set. So this is the third order model. So in the third order model, we only had to calculate up to K4. Okay, so K1, K2, K3, and K4 was there. So you can see the A matrix. This was the A matrix, which was 3 by 3 matrix. And we calculated the eigenvalues of A. And if I check it, let's say if we check it, I run it, and the eigenvalues of A were like this. Okay, so is it stable or not? This is the third order system, remember, without exciter. Is it a stable system? Or an unstable system?
Stable system.
It's a stable system because you can clearly see these are the pole locations, and all the poles you can see they have a real part with negative sign. So if you plot them on the S domain, so you will see that all of them lie on the left half of the S plane. So thus the system is stable. Actually, how you can calculate it by hand, that is an interesting thing to do. In MATLAB, we can easily do it like, you can simply type EIG of the matrix, system matrix A, it will give you the eigenvalues. Otherwise, if you want to calculate by hand or check it by hand calculation, then simply what you have to do, you have to calculate this determinant of S, where S is the Laplace operator, SI minus A. So first of all, you have to form this SI, or I is an identity matrix or unit matrix. A is your system matrix. S is the Laplace operator. Okay. So simply you form this Si minus A matrix and then you calculate the determinant. So all the same, we will get the same value of DD that you get here. So this is nothing but saying that this is the eigenvalues. So if you want to cross check with your hand calculation, you can do that. But because we have MATLAB, so we are simply taking the help of the command, built-in command. Okay, so, and that means this means nothing but you are actually looking for the roots. Okay, so determinant of Si minus A should be equated to 0. And then you should solve for S. So solve for S. These are the roots for your characteristic polynomial. Okay. So now this is the third order system. We already did it before mid, but now we have completed the fourth order modeling part. We have included the exciter block. We have built the 4x4 system matrix today, and so today we will be interested in the fourth order model, and it is the same one. It is the same data set as we used for the third order model. Okay, are you seeing the fourth order file, the linear SMIB fourth, or you are still seeing the linear SMIB third?
That
No, voice is broken. Still broken.
Fourth, sir.
Okay. So now let's say, okay, so what we have done in the fourth linear SMIB fourth file, M file, besides calculating K1, K2, K3, K4 as before, we have incorporated this K5 and K6. Okay, so we are formulating K5 and K6. So you can see we derived this formula that it was VD0 by absolute of VT0 into P1 plus VQ0 divided by absolute of VT multiplied by P2. This was K5, which was the coefficient of del delta, and this the K6 was the coefficient of del EQ prime. So that was VQ0 divided by VT0 multiplied by P3, where P1, P2, and P3 were like this. Okay, so then we have arbitrarily set some voltage regulator parameters, like the gain of the voltage regulator is set as 100. The time constant of the voltage regulator is set as 0.01. These are available in the literature or even in the book. You can find these values. So when we incorporate these values, then we would be able to formulate the A matrix. Now it would be 4x4. And now if we run it, before running, let's quit it. Okay, if we run it, then this is our eigenvalue. So now, can you see the eigenvalues, 4 eigenvalues?
Yes, sir.
Okay. So is it stable or unstable?
Unstable.
It's unstable. So this is the problem. Okay, so we have incorporated the exciter model. Before incorporating the exciter block with the same set of data, that means at the same operating point, the generator was stable. The third order generator dynamics was stable. Unfortunately, with this set of data, additional set of data of K and TA alone, all the other data sets are taken from the third order model. All the other values are exactly same. Simply, we have introduced K5 and K6. We have introduced the voltage regulator block parameters, and we have updated the A matrix. And we see that the system has become unstable. Okay. So what we would have to do next to improve the stability of this A matrix, where we have incorporated the exciter. This is exciter block. So in incorporation of exciter actually provides some negative damping to the system. So when you incorporate exciter into your synchronous machine block, you actually introduce some negative damping. And to get rid of this negative damping effect, what we would do next, we would go and design the power system stabilizer, which would ultimately again bring us the stability for the system under consideration. So our next topic, inshallah, will be the consideration and the design of the power system stabilizer. Okay. What you can do, you can check this A matrix with the derivation that I did in the slide. You can check the A matrix, you can check the eigenvalues. You can also play with these two parameters. Okay. Someone might say, well, why we are choosing this? I may choose any other values, but of course, the values should be taken from some practical exciter model available. Okay, you can't choose like 10,000 here and minus here. Okay, no, not something impractical. The values should be practical. So the value that I have taken, it is one of the practical set of data available for the IEEE ST1 simplified exciter model. You can change it a little bit and you can see what happens with the stability. Okay, you can play with the values. So that's it for today. So what we have observed today, what we have done today, actually, we started with the exciter simplification, exciter block simplification. And we did the simplification for the DC1A type. So the DC1A type, after we simplified that, so DC1A was simplified, and then we linearized it. Then we linearized it. Okay. And in between that, we also showed how to find out how to initialize this. We got three additional states. And we discussed a little bit that how we can initialize those state variables for this DC1A model. But that was again nonlinear type. We linearized it. And then we shifted from this DC1A to ST1A, but a much more simplified version. Then we calculated the del VT. We incorporated this del VT. We introduced K5, K6, all these things. And then we made the A matrix. Now the A matrix was 4 by 4. We checked the stability for the 3 by 3. We found that for this specific operating point, the system was small signal or small disturbance stable. However, with the inclusion of this exciter block over here with this set of parameter, the same system, 3 by 3 system, which has now become 4 by 4, becomes unstable. And that is because of the introduction of the negative damping created by the exciter to the system. How it actually affects, we will discuss it with the help of the block diagram. In the next class, we will start with some block diagram, which is famously known as the Heffron-Phillips model. And it is a very much famous model, which you will find in most of the papers dealing with single machine infinite bus system stability scenario. So that's why, because the Heffron-Phillips model actually takes into account of this exciter. It doesn't consider DC1A or any other exciter. So it considers actually the simplified version of ST1A exciter. This is one of the main reasons why we chose this one. Okay, why we chose this one as the exciter model to continue in our course, because we are interested in development of the Heffron-Phillips model, and that is possible with the simplified version of the IEEE ST1 exciter. Okay, so with then after we start the Heffron-Phillips model, then from that we will see how actually exciter, in the incorporation of exciter, actually hampers the damping scenario of the system, and then we will be slowly moving into the design part of the power system stabilizer, inshallah. Okay, any question? Any query related to exam? Any confusion mid-exam? Nothing. Okay then, so let's stop it here. And again, let me announce it. This class will be shifted from the next week on Mondays. Okay, so next week there won't be, from next week onwards, there won't be any class on Wednesday evening. The classes will be shifted on Monday evening. Okay, so thank you again for coming to the class. Let's see you all inshallah on Friday. Assalamu alaikum.